Well, welcome everybody to this Fireside chat session. And despite the doors being open, I think we're probably loud enough just to get going. So I thought it'd be worth, in 30 seconds, setting the scene.
Yeah.
There's some themes emerging in the past few days. One is it's not quite the NISC machine is dead, but I think we've seen some real incentives for saying that mastering error correction is important. I think another thing we can say is that I wouldn't say people are going soft on quantum advantage. I think the neatness of the expression quantum advantage is being undermined slightly because people are really saying the important thing is making quantum computers that are useful, and useful quantum computers may actually be closer than we thought. So I think that's an interesting trend. It's also very interesting to be talking to Steve, who I'll formally introduce, he already has been, but is not with a quantum computing company. So I think this is a very interesting turn, which is, it shows not just that the technology is growing up, but the industry is growing up. So we love technology readiness levels. I think industry readiness levels are much better. And the fact that we've got a company as successful as Riverlane specializing in this area is an interesting observation. So I'd like to invite Steve Brierley, CEO of Riverlane, to, in true fashion, join us on our quest for the Holy Grail. And not to quote Monty Python, he's not allowed to say, "We've already got one, it's very nice." Right?
Right.
Steve, maybe you could start by telling us what is error correction on quantum hardware?
Yes, great. So we just had the last panel talk about the importance of error correction. And I think that the question then is, well, how do you implement error correction in quantum computing? Turns out that it's actually a real-time data processing problem. So as Roger was saying, Riverlane is actually a classical semiconductor company working in quantum computing. So we don't build qubits ourselves, we build chips that process the data that comes out of the quantum computer. I think the really interesting thing about error correction is that it sits inside the clock cycle of the quantum computer. So every operation, some of the qubits are measured. This data tells us something about what went wrong, something about which bits were flipped or which error occurred. And then we have to infer, given this data, the most likely error. So we solve this inference problem and then make a correction. And so this needs to operate at a rate of megahertz. So it needs to keep up with the syndrome generation rate of the quantum computer, so the data coming out. Because if you can't, then the whole thing grinds to a halt. So we're a chip company at heart. Yeah.
So people will notice, this didn't happen 2 years ago, but every time the door opens, you hear a noise. Now, in case you haven't realized, that's something out there called a quantum industry. All right, we haven't had one before. All right. So you're a specialized company in this great new industry, which does exist now. In terms of error correction, what's the state of the art? And where have we got to get to? Because we've got people relying on you. Other businesses are going to come to fruition if you make the progress you're hoping to make.
Yeah, so I think there are really three things that need to be done in order to build an error-corrected quantum computer. So the first is on the qubit side. So we need qubits that are good enough. So we need to get the physical error rate below the threshold, the QEC threshold. That's the point at which improving fidelities is diminishing returns. So at that point, the challenge becomes scaling up number of physical qubits. So the first thing is on qubits. The second is on improving how we implement quantum error correction. And so there are lots of different codes. We're still figuring out the best way to map the code to the underlying physical qubit, how to implement logic, and so on. So that's a really big problem space. And then the last is on the classical processing. So being able to process this data fast enough. That's actually a huge challenge. If we fast forward perhaps 10 years, we'll be at millions of physical qubits. The amount of data coming out of the quantum computer will be on the order of 100 terabytes per second. That's like Netflix global streaming, and you need to process that right next to the quantum computer. And if you don't, the whole thing grinds to a halt. So there are, I think these are the three big challenges. the super exciting thing, I mean, this has just been a wonderful year, I think, for quantum error correction. You've seen people improving physical fidelities, scaling up number of physical qubits across multiple different qubit types. We're seeing advances in the codes that are reducing the overhead of the logical to physical ratio, so how many physical qubits you need ultimately. And we're seeing teams improve how we implement error correction to reduce the resources that are needed at the underlying physical qubit rate. And then, of course, the work that we've been doing on real-time data processing.
So just thinking about performance, if I look at the UK quantum missions and what I'm computing, which says by 2035 we'll have access to machines capable of 1 trillion operations. You've mentioned throughput and so on. I mean, is that trillion a specific figure, or is it just a big one? We're supposed to go, ooh, that's impressive. I mean, what's the importance of a trillion in terms of what suddenly we can do?
Yes, I really like the UK quantum mission in that it gives a very clear metric. So it's how many quantum operations can you do before the system fails? And ultimately, that's the thing that the user of a quantum computer cares about. Of course, you care how long did that calculation run for as well. So I think it was quite nice just to say, well, let's get it to work first, and perhaps we'll worry about speed later. So a trillion is a really great milestone in that we know there are some huge applications for such a device. So there are quantum algorithms that have already been costed up that have about that many operations, even without the continued improvements in algorithms. So I would very much expect the number of operations that are needed for a quantum algorithm to continue to reduce, and we've seen that progress over the past 10 years been very impressive. So you get applications, in computational chemistry, in material sciences. It's kind of clearly gone beyond the capability of any supercomputer. And then I think the other nice thing about the UK mission was that it set a really tight deadline for the first error-corrected quantum computer of 1 million error-free operations by 28, which is like less than 4 years now. So we need to really get on with it. So I like that sense of urgency. It requires error correction, so it requires building a whole system, which is really a phase shift from the NISQ era, if you like, the pre-error corrected era.
So we've been used to over the years, I'm surprised saying that, but it has been years now, hasn't it, since you created Riverlane, hearing you talk about what quantum computers do as an applications guy, and we don't imagine you encumbered by a dilution fridge and all this dreadful bulky hardware, and suddenly you're a chip company. So we've got to get used to more thinking about hardware, Steve. But when are we going to see the chip? What's the story? I mean, is this something which has to have dedicated hardware? Is this absolutely central to what error correction is about?
So if you stop by our stall, you can see the world's first error correction chip.
I just haven't been there yet.
I would love to solve the problem in software, but it's just not possible. And that really comes from this realization that it's a real time. So no interrupts, no checking emails between solving an error correction problem. It's a real-time processing problem with a huge amount of data, ultimately. And so it's just cheaper to build a chip. Most of our solutions right now are on FPGAs. These are just reconfigurable systems, and that's just a matter of volume. As we scale up, there will be hundreds of chips solving the error correction problem, and so then it makes sense. In every quantum computer, and there'll be many quantum computers, and so we quickly get to the space where it's worth spending the upfront cost of developing a dedicated chip for each solution. We're starting to see, I think, as you put it at the beginning, sort of maturing of the ecosystem where we actually care about how much is this going to cost to build this system. And if you simply took the solution as it is today and scaled it up, it would be hugely expensive. I mean, each FPGA is around $1,000 to $10,000. You had hundreds of these for every system. It could quickly get to the point where it becomes prohibitively expensive. So yeah, I think there's a real sign of maturity in ecosystem.
Okay, and you and I were chatting about this beforehand, but I've got to say I didn't know the answer because I was racking my brains. But one of the things in the UK we've been keen to do is work on developing this industry. National Quantum Computing Centre is now running a testbed program with 7 different platforms. It's going to be fascinating to see in one place this diversity of approach. And I said to you, because I didn't know the answer, well, I hope this supply chain idea is working out. Are you involved in any of them? Because if the answer is no, are you involved is a big question. Can you tell us what your involvement is, given that there are some very different platforms in there?
Yes, absolutely. So we're supplying error correction to 3 of the testbed systems. So this will allow us to, allow the NQCC to evaluate these systems for the next generation. There was a question in the earlier panel, what's the value of current quantum computers? Well, it's actually to develop the next generation of quantum computers. So we need to build smaller quantum computers in order to understand how to build quantum computers, how errors occur in the data, how to build the whole system together. The notion that you could, I think, build lots of components and then just assemble them at the very end is I think, a fallacy. What we know from large-scale compute is that every time you scale up by a factor 10, something breaks, which was previously fine. And so we just need to go on this journey in scaling up quantum computers. So I think the NQCC program is great, primarily because it's government doing what it should, which is buying stuff, buying early technology. That's creating then a demand for companies to deliver, and really deliver, right? You can't just say you're going to do something; you have to show up and deliver it. So that is pushing the ecosystem forward. And I think if you look back at the development of the semiconductor industry, a lot of these trends that we're seeing in quantum played out 50, 60 years ago. You had NASA buying early integrated circuits. You had an increasing specialization in the supply chain when companies like TSMC and ASML were developed to really focus in on the hard bits that could be shared across an ecosystem. So we're seeing that now in quantum, and I think it's a great initiative by the UK government. To quote Meatloaf, 3 out of 7 ain't bad. I don't think that's quite right. But, to actually be supplying, because it's a procurement program, as you say, and you're not doing this for love. That's right. And
the people who've won these programs are your customers.
Yes, and they have a choice. They can either build error correction themselves, or they can buy it from somebody like Riverlane. And increasingly, hardware companies are looking to be more efficient, to move faster, to save money, and so are outsourcing parts where they can. I was recently in Delft working with Leo DiCarlo, and I can't tell you how much his eyes lit up when he was explaining that you could now buy a chip holder on the internet. And he used to have PhD students build fashion one by hand, and it took months. I think this is just an example of how this supply chain is accelerating the whole ecosystem. And so as more companies come in who specialize on parts of the value chain, I think we're going to see this next wave of innovation and acceleration happening in quantum computing.
Great. I mean, there is a question come in on the supply side of the semiconductor industry. Maybe, I think you've answered that to some extent, but maybe in the last minute, what next? Because it is a forward-looking conference.
Yes, absolutely. So
we've had so much now to report on, but what next for Riverlane?
Yes, we built the world's first error correction chip. To get to 1 million error-free operations, we need to build the megaquop system, so million quantum operation system. So that involves many chips all working together. So if you think of the analogy of the decoder chip is like the GPU of AI. So the next stage for us is to build the H100, the board that contains many, many GPUs all working together to solve a much larger data processing problem. So we're planning to release that in 26. It's going to take some time to build. teams on it right now. It's a great challenge, kind of bringing together skills in quantum error correction. So some of the top people who were solving error correction at companies like AWS and for IBM and Google, working together with people who've built dedicated chips before. So people like Kauser, who leads our silicon team, who we recruited from ARM. So built real-time error correction systems for other industries like the automotive sector. And so this combination of skills is a really exciting time, and I think that kind of intersection is really where the magic is happening right now at Riverlane.
I think what was encouraging to me is you went through at least 5 minutes without saying the word quantum. I mean, these are real problems. They're much broader than the physics, which is happening in the qubit itself, and they're taxing scientists and engineers across many, many companies. So, no, thank you for I think helping us on our quest. Thanks very much, Steve.
Okay, you're right.